Here's a brief video on free body diagrams. So like let's say we have an object falling, okay? So we have a falling, I don't know, cat, okay? Doesn't really matter what it is because you guys can get fancy with it if you want to, but basically all I do is just draw a box that's representing whatever object it is, which in this case is a cat. So I have a falling cat, and you just have to think about what forces are acting on the cat if he's falling. So of course there's force of gravity, always going to be force of gravity unless you're like in space or something. So there's my force of gravity labeled as F sub g, and notice my force vector is originating from the center of mass of the object. And you have to, is there anything else acting on the falling cat? And there is, air resistance, which is a frictional force. Okay, so I'll also have that originating from the center of the object. So there's my frictional force F sub F. Okay, now these forces. They are vectors. Okay, and these are free body diagrams. So these are vectors, and they're just representing the forces acting on the object. So in this case, we have the two lengths are equal to each other. So that means that these two forces are equal to each other because the length of these vectors is representing the magnitude of the force. Okay, so these two are roughly the same length, so that means that they're roughly the same magnitude. Okay, so like let's say we have pushing a car to where it's accelerating. Okay, so we have the car, it's being pushed. Okay, so there's my car. It is being pushed, so that's an applied force. Normally I have this showing as my applied force usually going to the right. Usually, I don't know why, I just go with pushing things to the right. And then we have the force of gravity going down. Okay, now making this just larger just to kind of show that the weight of the car is going to be quite a bit more than the force that I'm pushing the car with. And also, if force of gravity is going down, these forces should be balanced. So that means I'm going to have my normal force about the same length as my force of gravity. Okay. Now this car is going to be accelerating. I'm going to say it's accelerating to the right. So I'm just going to show the acceleration is going to the right. It's not really part of the free body diagram because it's not a force, but you can put it off to the side like this. And this can be a good practice to get into once we start getting into more difficult problems. So here's my normal force going up, same magnitude, opposite direction as the force of gravity. There's my applied force. There is going to be a frictional force, but since it is accelerating to the right, that frictional force should be less than the applied force. Okay? One last thing, let's say we have an object that's on a ramp. Okay? There should be a little bit of contact there with the box and the ramp. So let's make that right there. There's my ramp making contact with the object. And so this is just falling down a ramp. Or I guess rolling down a ramp. Okay? So here's my force of gravity going straight down. Doesn't matter if it's on an incline or not. Here is my frictional force. Since it's going down the ramp, the frictional force is going to be going in the opposite direction of the motion. And then I have the normal force, which is perpendicular to the surface. Okay, so there's three examples of free body diagrams. So just remember that that the length of the vector is the magnitude of the force, and the direction of the vector obviously represents the direction of the force as well. And usually these forces originate from the center of the object, the center of mass. All right, and that is free body diagrams.